Okay, it is time for the last section of Chapter 7. Get excited. Using or applying exponential and logarithmic functions. This is great because we're going to actually use, in word problems, some of the logarithms and exponential functions that we've worked with, and specifically we're going to learn a new exponential growth and decay formula. So, the vocabulary you need to be on the lookout in this section is rate of continuous growth, rate of continuous decay, and then logistic growth model, which we may or may not get to in this video. But if we don't get to it in the video, then we'll cover it in class. So exponential growth and decay, these are going to be two new equations or two new functions to model exponential growth and decay. Exponential growth can be modeled with this equation. F of x equals a times e, there's that number e again, to the k times t. A is my starting value, just like it was back in section 1. T is the time in years. And k is a constant. Depending on the question, they'll give you that constant or you'll be able to figure it out. And it represents a rate of continuous growth. This is what makes this one different. And the decay equation is almost the same, except instead of a positive exponent, we have a negative exponent, and that represents continuous decay. So do not confuse these with what we learned back in section 1, which was exponential growth and decay that had a constant percent of increase or decrease. So it increased by 10% per year, or it decreased by 5% per month, or something like that. That's different than continuous growth or continuous decay. So let's take a look at an example of exponential decay, and this is going to be continuous exponential decay. We're going to be talking about geology. So the half-life of sodium-22 is 2.6 years. Remember that half-life means how long it takes the amount that I have to cut itself in half. So it takes 2.6 years for sodium-22 to cut in half. Determine the value of K and the equation of decay for sodium-22. All right, so A is the initial amount, right? But we don't know the initial amount here. So we're going to think about what we could do. The amount that would be remaining after 2.6 years would be half of that, because 2.6 is the half-life. So if A is my starting amount, the amount that I would have left after 2.6 years is 1/2 times A. So I know I'm using decay, because half-life is always decay. It's how long it takes it to cut in half, to reduce by half. And then A is my starting amount. 0.5A is how much I have left after 2.6 years. Notice I put 2.6 in for my time because I'm only dealing with one half-life, and I need to solve for K. So I'm going to divide each side by A, because basically if 0.5 times A is equal to this E expression times A, they both have to be equal. And then, because here I have a variable in the exponent and I have a base of E, I'm going to take the natural logarithm of both sides, just like we did in the last section. And then the natural log of E, those are inverses, so they undo each other. I'm left with negative 2.6K. And I'm going to divide both sides by negative 2.6. And then I'll use a calculator to get this value. So the value of K is about 0.2666. Notice we're still rounding to the nearest 10,000. So the value of K is this value, and so my equation would look like this. So I could put in any initial amount at any time and figure out the amount that would be left. Okay, so you guys try this one, another half-life problem. All right, your answer here should be C. All right, and there's the work that you can follow through. Feel free to pause if you need to take a look at that. All right, let's take a look at another example. This one uses the idea of carbon dating in geology as an example. It says a geologist examining a meteorite estimates that it only contains about 10% as much sodium-22 as it would have when it reached the surface of the Earth. How long ago, according to this model, would the meteorite reach the surface of the Earth? So the formula for decay, because if there's only 10% as much, that means it's gone down. So we're using the continuous exponential decay. We want to find how long ago, so we need to find time. It says let A be the initial amount, so that's my starting amount. How much is left, that's Y, after 2 years is 10%, or 0.10 of whatever A is. So again, we don't know A, but we know that what's left over is 0.10 A, or 10% of A. So if we're going to solve, we're going to set up our equation. Where did we get this number? We got it from example 1. If you go back to example 1, we have the K value for sodium 22. That's always going to be the value of K. Then I replace Y with 0.10 or 0.1 A. Remember, that's 10% of A. So the leftover amount is 10% after this decay process happens. So when I divide each side by A, or when I set the coefficients of A equal to each other, I get 0.1 is equal to E to this expression. Take the natural log of both sides because I have a base of E and I have a variable in the exponent. And then solve just like we did in the last example. Divide both sides by negative 0.2666, and I get a value for T, which is about 8.64. You'll need a calculator for these problems. So that means it reached the surface of the Earth about 8.6 years ago. So if we want to check, we can use the formula and plug in 8.6 to see if we get 10% of what was left. And we'll just assume, let's say we had an amount of 1 to start with. So if I plug in 1, am I going to get 10%? And it turns out that I do. So if I start with 1 and I use 8.6 years, I get 10%, which matches what the problem said to begin with. Okay, why don't you guys try this one about health? In this case, our answer is D. All right, here's the process to get D, about 18.58 hours. Again, we got our value of K from a previous example, from the first check your progress example. So hopefully you are taking good notes and writing that down. All right, let's take a look at population. Population is a very common example of exponential growth and decay. It says in 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion. Determine the value of K, which is the relative rate of growth for China. So here we are growing, and we're assuming that it's continuous exponential growth in this case, because they're asking us for a value of K. And so what I'm going to do is, I know what it is right now, 1.32 billion, but we're going to leave the billion off. We'll just know that we're plugging our numbers in billions, so our answer will be in billions. 1.32 and then 1.26 was my starting value because we're measuring since the year 2000. And then I put in 7 for the time because 7 years have passed between 2000 and 2007. Divide both sides by 1.26. Take the natural log of both sides so that I can get this variable out of the exponent. So I end up with 7K is equal to the natural log of this quotient. And then I divide by 7. And use a calculator to get my value of K, which is 0.0066, or about 0.66%. So we are using the same problem, but when will China's population reach 1.5 billion? So using my same formula, now I know the value for K. So I plug in the value for K. I want to know when it will be 1.5 billion, so I want to know when that's going to be the final amount. My starting amount is still 1.26, and T is my variable because I need to know when. I'm solving for time. Divide both sides by 1.26, and then take again the natural log of both sides because I have a base of E and a variable in the exponent. So I have the natural log of 1.1905 is approximately 0.0066 T. I divide both sides by 0.0066. And then use a calculator again to get your value. So that means 26.42 years. Oops, sorry. So it'll reach that in the year 2006 because remember our starting point is the year 2000. So if 26.4202 years have passed, it will be in the year 2026 that China's population would reach that amount. All right, same problem, another question. When will India's population surpass China's? It says India's population in 2007 was 1.13 billion, and they give us an equation for India's population. So we don't have to worry about finding K, they give it to us. We want to know when India's population will surpass or be greater than China's population. So we set up an inequality, right? I want this is India, and this is China. I need India to be greater than China, or I need China to be less than India for the question that they're asking me. So in this case, I have both sides. I have a base of e, so I'm going to take the natural log of both sides. And I'm going to use the product property of logarithms, okay? So notice here I have the natural log of 1.32 times the expression of e. So I have to split those up. Natural log of 1.32 plus the natural log of e is less than the natural log of 1.13 plus the natural log of e. In this case, natural log and e are inverses, so they undo each other, and I'm just left with the exponent. Same thing here. And then I just need to get both of my t terms on the same side, so I'm going to subtract 0.0066t from both sides. And I'm going to subtract the natural log of 1.13 from both sides as well. And then I end up with this difference, and then I have to divide that by 0.0084. So I'm going to use a calculator to evaluate the left side here, and I get about 18.5. So that means 18.5 years. Remember, with word problems, we always have to keep track of our units. So India's population will be greater than China's in 18.5 years, or partway through 2025. All right, please try. This one is about the population of Alaska, so you're going to start out by finding the value of k like we did in part A of the previous example. All right, your answer here should be B. Okay, this is the equation you should have set up. I'm not going to show you the whole process because my tablet is losing its mind and I'm having a hard time writing, but this is how it should have started. You should have divided both sides by 620,000, then taken the natural log of both sides, and then you'll end up dividing by 6 to get your value of k, which should be this. Make sure you write it down because you need it for the next question. All right, so same situation, population of Alaska. When did it reach 700,000? All right, it should reach 700,000 in the year 2009. All right, this is the equation you should have set up, again using the k value from part A, and I need to solve for t. So you should have divided both sides by 620,000, taken the natural log, and then divided by the k value, and you get about 9.386 years. One thing I wanted to say about these problems is it's better if you can leave everything exact until the very end and evaluate at the end, because then you only round once instead of rounding in multiple steps all of the way through. So in about 9 years, 9.386 years, so that means in the year 2009, Alaska's population would reach 700,000. All right, last but not least. All right, in this case, D would be your answer. All right, this is the inequality that you should have set up, and it should have given you, saying the amount of years after 2006. You should have gotten something like 27, and that would give you in the year 2027. If you need to see the steps to work this out, you can ask me in class. Again, my technology is failing me a little, so having a hard time writing, but I can show you that process. It's just like part C of example 3. All right, last but not least, we might not get to the problems for this, but this is called the logistic growth function. And basically just what I want to point out here is that sometimes an exponential growth or decay model doesn't always make sense, because if I look at this model up here in the picture, the years since 2000 and the population, an exponential model shows that the population will continue to grow without bound. And in this example, they say, according to this, the population of Georgia, which is one of the states in the U.S., would be 1 billion just in that state. That's not totally logical. Populations can't grow infinitely because there are limitations like food, supplies, living space, diseases, people die, right? So instead of using an exponential model all the time, sometimes we use something called a logistic growth model. It represents growth that has some limiting factors in it, like disease or limits of resources or people moving away or things like that. These are actually the most accurate models, although they're a little harder to work with. So this is what the logistic growth function looks like. In class tomorrow, if we have time, we'll look at how to do some problems with this or how to interpret it a little bit. For now, I just want you to know that it exists and that it's a better model than exponential, just a